Imagine transforming raw data into actionable insights with just a few keystrokes. The tools for calculating odds ratios have come a long way from pen and paper methods, offering data scientists a range of options to suit their needs. But with this power comes a critical question. How do we ensure we're using the right technique for our specific analysis? Let's start with the basics. Manual calculation of odds ratios using a 2x2 contingency table remains a fundamental skill for any data scientist. This method involves organizing data into counts of occurrences and non-occurrences for each group being compared. By calculating the odds for each group and then dividing them, we arrive at the odds ratio. While this approach is straightforward, it becomes time-consuming and error-prone when dealing with large datasets or multiple variables. Enter the world of statistical software, where efficiency meets precision. Popular platforms like R, Python, and SAS have revolutionized the way we handle odds ratio calculations. In R, for instance, the epitools package offers the odds ratio function, which can be applied directly to a contingency table. This not only yields the odds ratio, but also provides confidence intervals, adding a layer of statistical rigor to your analysis. Python users aren't left behind, with the stats models library offering robust tools for odds ratio calculation through logistic regression models. By fitting a logistic regression and exponentiating the coefficients, data scientists can obtain odds ratios for multiple predictor variables simultaneously. This approach is particularly valuable when examining the influence of various factors on an outcome. For those working in clinical research or other fields where SAS is prevalent, the PROCY logistic procedure is a powerhouse tool. It not only estimates logistic regression models, but also outputs odds ratios directly in the results. This feature allows researchers to adjust for confounding variables and obtain confidence intervals, all within a single procedure. While these software solutions offer tremendous power, they also require a certain level of expertise to use effectively. For those seeking a quick estimate or working with simpler data sets, online calculators for odds ratios can be a tempting option. However, it's crucial to approach these tools with caution. Many online calculators have limitations, such as the inability to adjust for confounding variables or provide confidence intervals. While they may serve for initial exploratory analysis, relying solely on these tools for critical research could lead to oversimplified or potentially misleading results. As we dive deeper into the world of odds ratio calculation, we encounter more advanced techniques that allow for nuanced analysis. Calculating adjusted odds ratios through logistic regression is a prime example. This method enables researchers to control for confounding variables, isolating the effect of a specific factor while accounting for the influence of others. In complex studies where multiple variables may impact the outcome, this approach is invaluable for obtaining accurate and meaningful odds ratios. Continuous variables present their own set of challenges and opportunities in odds ratio calculation. Rather than comparing distinct groups, we're often interested in how the odds change with each unit increase in a continuous predictor. For instance, when examining the impact of age on loan approval, we might find that for each additional year, the odds of approval increase by a certain percentage. This interpretation requires careful consideration and clear communication to ensure stakeholders understand the implications. One powerful technique that bridges the gap between statistical analysis and interpretation is the exponentiation of coefficients obtained from logistic regression. This method provides a straightforward way to interpret the impact of predictor variables on the odds of an outcome occurring. By reporting these exponentiated coefficients alongside their confidence intervals, data scientists can present a comprehensive picture of the relationships within their data. As we navigate this landscape of tools and techniques, it becomes clear that the choice of method for calculating odds ratios isn't just a matter of convenience. It's a critical decision that can significantly impact the validity and interpretability of our results. The best practices for efficient and accurate odds ratio calculation involve a thoughtful approach that considers the nature of the data, the complexity of the analysis, and the intended audience for the results. But even with the right tools and techniques, data scientists can fall into hidden traps that compromise the validity of their odds ratio analysis. Let's uncover the sneaky pitfalls that can turn our insights from illuminating to misleading and learn how to navigate these challenges with confidence. One of the most common mistakes in odds ratio analysis is misinterpreting the odds ratio as a relative risk, especially when the event being studied is not rare. This error can lead to a significant overestimation of the strength of an association between variables. For instance, if a study finds an odds ratio of 2.5 for a particular risk factor, it would be incorrect to conclude that individuals with this factor are 2.5 times more likely to develop the condition. This misinterpretation can have serious consequences, particularly in medical research, where accurate risk assessment is crucial for patient care and public health decisions. To avoid this pitfall, it's essential to communicate odds ratios clearly and distinguish them from relative risks, especially when dealing with common outcomes. One effective strategy is to convert odds ratios into more intuitive measures, such as expected frequencies or percentage changes in risk. This approach can help bridge the gap between statistical findings and practical implications, making the results more accessible to non-technical audiences and reducing the likelihood of misinterpretation. Another major challenge in odds ratio analysis is the impact of confounding variables. These are factors that influence both the predictor and outcome variables, potentially creating spurious associations or masking true relationships. For example, in a study examining the link between coffee consumption and heart disease, age could be a confounding variable if older individuals are more likely to drink coffee and also have a higher risk of heart disease. Failing to account for such confounders can lead to inaccurate odds ratios and flawed conclusions. To address this issue, researchers must be vigilant in identifying potential confounding factors and employ appropriate statistical techniques to control for them. This may involve using multivariable logistic regression models or stratified analysis to adjust for known confounders. Additionally, careful consideration of study design and data collection methods can help minimize the impact of confounding variables from the outset. Multicollinearity presents another significant challenge in logistic regression and odds ratio analysis. This occurs when independent variables in a model are highly correlated with each other, making it difficult to isolate the effect of each variable on the outcome. In such cases, the calculated odds ratios may be unstable or misleading, complicating the interpretation of results. For instance, in a model predicting customer churn, variables such as time since last purchase and customer engagement score might be highly correlated. This multicollinearity could lead to inflated or deflated odds ratios for these predictors, obscuring their true relationship with the likelihood of churn. To mitigate this issue, data scientists should carefully examine the correlations between predictor variables and consider techniques such as principal component analysis or regularization methods to address multicollinearity. Interpreting odds ratios in case control studies poses unique challenges due to the retrospective nature of these studies. Case control designs are particularly prone to selection bias, which can distort the calculated odds ratios. For example, if cases, individuals with the outcome of interest, are more likely to recall or report certain exposures than controls, this recall bias can lead to an overestimation of the odds ratio. To minimize these biases, researchers should strive for rigorous study design, including careful selection of cases and controls, standardized data collection methods, and consideration of potential sources of bias in the analysis and interpretation of results. It's also crucial to acknowledge the limitations of case control studies when reporting odds ratios and to interpret the findings in the context of other available evidence. The rarity or commonness of an outcome can also affect the validity of odds ratio interpretations. When dealing with rare outcomes, odds ratios can provide a reasonable approximation of relative risk. However, for common outcomes, typically those occurring in more than 10% of the population, odds ratios can substantially overestimate the relative risk, leading to exaggerated conclusions about the strength of associations. To address this limitation, researchers should consider alternative measures such as risk ratios or risk differences when analyzing common outcomes. Additionally, it's important to clearly communicate the prevalence of the outcome when reporting odds ratios, allowing readers to gauge the potential for overestimation. Proper study design is fundamental to producing reliable odds ratios. This encompasses not only the statistical analysis, but also the entire research process, from hypothesis formulation to data collection and interpretation. Researchers must ensure that their study design minimizes biases, adequately controls for confounding variables, and uses appropriate statistical methods to produce valid odds ratios. This may involve careful consideration of sample size and power calculations, randomization techniques in experimental studies, and the use of validated instruments for data collection. Furthermore, pre-registration of study protocols and analysis plans can help reduce the risk of selective reporting and post hoc adjustments that may inflate the significance of odds ratios.